Hello everyone and welcome back to the Jamaican Geologist YouTube channel. This is episode 8 in the Geology Foundation series, and today we are starting the part of the series where we will focus on each category of rock in greater detail than we did in our little introduction to rocks in our previous episode. Today's episode is all about igneous rocks, the origins, subclasses, the minerals that make them up, and the odd sounding words we use when we are describing them. Like all rocks, igneous rocks tell a story about our planet. But also, as with many topics discussed in the series so far, you will start to realize that they play a role in society and culture too. So, let's get started. So what are igneous rocks? Well, the word igneous is derived from the Latin ignis, which means fire. Think about it for a second. There are common words we use like ignite, like when you set something on fire, or ignition, like when you say you put the key in the ignition, you ignite the fuel in your vehicle so the car can drive and you can move. And even more poetically, you are in love with someone and you separate for a while, and then one day you are reunited. People say you ignited or reignited an old flame. There is an old saying in Jamaica, old fire tick easy to catch, which is used to explain this phenomenon of renewed love interest. Anyway, the point is the root of the word igneous is fire. So in a way, we can kind of think of them as heat or fire rocks. But let's look at a more formal definition. The Oxford Dictionary of Geology and Earth Sciences defines the word igneous as applied to one of the three main groups of rock types: igneous, metamorphic, and sedimentary, to describe those rocks that have crystallized from magma. So magma is the fire part. So igneous rock originated from magma. They are formed from the crystallization of magma. Alright, cool, but what does this all mean? Is there only one igneous rock and that's it? Or is there more to it than that? I think you know what the answer to this is. As we have seen so far in this series, things can get very granular. We will discuss this and more in the following segments. Alright, so we have established that in order for igneous rocks to form, magma has to crystallize. But what is magma again? Well, the Oxford Dictionary of Geology and Earth Sciences defines magma as a hot silicate, carbonate, or sulfide melt containing dissolved volatiles and suspended crystals, which is generated by partial melting of Earth's crust or mantle and is the raw material for all igneous processes. And then it goes on to talk about silicate magmas being the most common by far before it goes into talking about the different types of silicates and their structure. I won't get into all that here, as I did a video some weeks ago about mineral classification and I discussed silicates or silicate minerals at length. So anyway, to simplify the definition a little, magma is a molten rock beneath the Earth's surface. Okay, cool. But how does this rock or solid earth melt in the first place? Well, scientists have long proposed 3 ways for melting of solid earth to occur to facilitate the right conditions for magma to form. The first and most obvious case is the addition of heat, right? When rocks get extremely hot beyond any temperature you may encounter in your day-to-day life, even hotter than the temperature that you might encounter in your standard kitchen oven, they melt. The second case is a decrease in pressure. Deep in the earth, pressure keeps rocks solid, even if they're hot. If the rock rises toward the surface, pressure drops and the rock can melt without extra heat. The third way is the addition of water or flux melting. Water lowers the melting point of rocks. This happens at subduction zones where ocean crust and water sink into the mantle. Alright, we have established the ways in which rocks can melt to form magma, but let's take it a step further. Let's think about this for a second. There are two things I want you to think about. I want you to think about time and I want you to think about temperature. Let's use something simple like our kitchen. When you are cooking something, the temperature is important. I mean, if the flame is too hot or the heat is too high, then that can burn your dinner. The length of time is important. Keeping something for too long, no matter what the temperature is, can spoil it, or for too short and it's undercooked or half-baked. When cooking or baking, what is important is the right temperature at the right amount of time to achieve the perfect dish. But even with specific meals, different amounts of temperature and different amounts of time produce different results. This is the difference between hard-boiled eggs and runny eggs, or the difference between a well-done steak and a medium-rare steak. Okay, with this in mind, the question is, can this principle of different things happening at different temperature and over different periods of time be applied to rocks as well? And the answer is yes. Minerals tend to form or crystallize at different temperatures. So much so, we can predict what types of minerals will occur at what temperatures, and we will look at this in detail in the next segment. Before we move on to the next segment though, let's talk about the colors of rock-forming minerals in igniospectrology. There are ultramafic and mafic minerals, and these are dark to extremely dark minerals that form at very high temperatures. Example, olivine and pyroxene. Then there are felsic minerals, which are light colored, and these minerals form at lower temperatures, and an example is quartz. And then there is an intermediate sort of classification which form at moderate temperatures, not too high and not too low. An example of this is amphibole. We will explore this in detail in our next segment. So the Bowen's reaction series is a concept developed by Canadian geologist Norman L. Bowen in the early 1900s. Through lab experiments, he studied how minerals form as magma cools. He melted powdered rock, let it cool slowly, and observed which minerals formed at different temperatures. By repeating this process at various temperatures, he discovered a pattern in the order of mineral formation from magma, especially basaltic magma. And this pattern, called Bowen's reaction series, helps explain why certain minerals are often found together in igneous rocks and why others rarely occur in the same rock. It also shows how early earth or early formed minerals can separate from magma, a process called fractional crystallization, changing the composition of the remaining liquid. Today, Bowen's series is still used to understand how and under what conditions igneous rocks form, based on the minerals they contain. So the series looks like this. It may seem like a lot going on to the uninitiated, but it's quite simple. On the left, there is a scale that ranges from 800 to 1400 degrees Celsius. Of course, magma can be even hotter than this, but at this temperature, this is the range at which the fractional crystallization begins. Moving to the right, there is a discontinuous series. Here, the minerals crystallize one by one in a stepping sequence from the highest temperature, moving towards or downwards as the magma cools a little. Olivine crystallizes first, followed by pyroxene, then amphibole, and biotite. Back in the day when I did my Introduction to Earth Science Part 1 and 2 courses as part of my first degree in geology, I used the acronym OPAB, OPAB, to remember this. So it's olivine, pyroxene, amphibole, and biotite. Alright, cool. Further right, you have the continuous series. Calcium-rich plagioclase crystallizes at higher temperature, and sodium-rich plagioclase crystallizes at lower temperatures. Back in the day, for my exams, I would say to myself that calcium comes before sodium in the dictionary, so calcium-rich plagioclase crystallizes first, and sodium-rich plagioclase crystallizes as magma cools. The discontinuous and continuous branches are where the mafic or the dark colored and intermediate moderately colored minerals occur. At the lower portion of the diagram, there is a lower series where the felsic or light colored minerals crystallize. Here, the minerals orthoclase, muscovites, and quartz are crystallized. And for this, I just remembered the acronym OMQ. Okay, so far we have spoken about the different minerals in igneous petrology. Let's talk about the rocks themselves now. Broadly speaking, there are two main classes of igneous rocks. There are intrusive or plutonic igneous rocks and extrusive or volcanic igneous rocks. So what's the difference between them? Well, intrusive igneous rocks formed deep within the earth and extrusive ones formed at the surface. The names of these categories are quite self-explanatory, really. But how do we know the difference between them? Well, the general rule of thumb is that intrusive igneous rocks tend to have large crystals, while extrusive igneous rocks do not. The intrusive ones form as magma cools slowly beneath the earth, and as such, the crystals have more time to form. With the extrusive rocks now, the lava from volcanic eruptions cool rapidly, and they don't have large crystals visible. So let's examine a couple of rock types from my personal collections. This is diorite, and notice that this one has large crystals and it's an intrusive rock. Other intrusive igneous rocks include granite, gabbro, and peridotite. This is obsidian or volcanic glass. It's an extreme example, but we're going to use it anyway. Obsidian forms as lava cools so rapidly that crystals don't have time to form, resulting in a glassy or non-crystalline structure. Other extrusive rocks include scoria, pumice, and basalt. Just to note that all of these other extrusive rocks pictured, they have tiny holes in them called vesicles. The basalt and screen is known as vesicular basalt, and it came from this place called Black Hill in the parish of Portland in Jamaica, which is a window into Jamaica's volcanic past. And I will talk about Black Hill in another video outside of this series in the future. But anyway, what are these tiny holes called vesicles? What do they indicate? Well, vesicles are a common part of the structure of some extrusive rocks. Well, the holes form from lava containing gas bubbles. What sets the rocks with vesicles apart is that they tend to be lightweight and less dense than other igneous rocks. Before I move on, just a quick note on volcanoes. You can already tell that igneous rocks are formed or they're associated with volcanoes. But I believe that volcanoes deserve an episode for themselves in this series, so I will discuss volcanoes in a future video. So why does this matter? I mean, there is all this fancy science again. A guy crushed some rock into powder and melted it down and let it cool and try to see what crystals form first as the melt cools down. That all sounds well and good. And we put these rocks neatly into classes and know how to identify them. But what benefit does this have for the normal person going about their day? Well, let's start with the beauty and cosmetic industry. Have you ever heard of pumice stones? I know the ladies who are watching especially, they know what I'm talking about. Pumice stones are used mostly as tools by women for keeping their heels or the soles of their feet. In Jamaica we say foot bottom, but it keeps the heels and the sole of their feet smooth by removing dead skin. Pumice is an extrusive igneous rock, and those vesicles are what help in ridding the feet of that unwanted dry skin. Ever been to a spa and had a hot stone massage? I had a couple myself, and they do help in relieving the tension in the muscle. Well, the hot stones used by massage therapists are often basalt rocks, and basalts are the preferred one because they can absorb a lot of heat. Rocks like pumice and vesicular basalt also have horticultural applications. I know of them being sought after for the cultivation of orchids, and they are considered very good for the plant. Then, of course, there is the construction industry. Granite can be cut into slabs and used for kitchen countertops. And because of granite's durability, they are thought to last longer than your regular counters made from ceramic tiles or some other type of material. They can be quite expensive though, so sometimes they are used as a bit of a status symbol. Going back to pumice, because of the low density when compared to other rocks, they are used as lightweight aggregate in concrete mix design to produce lightweight concrete. And lightweight concrete is different from standard concrete in that it has a lower density, typically anything less than or anything under 2,000 kilograms per cubic meter. For context, standard concrete has a density of 2,100 to 2,400 kilogram per cubic meter. And then there is high strength concrete, which has a density often above 2,400 kilogram per cubic meter. And this is what I recall from working some years ago in a soils engineering lab. This topic can be for a whole other video, but high strength concrete is used in things like massive high-rise buildings on long span bridges. Standard concrete is used in things like sidewalks and driveways and normal residential buildings. And lightweight concrete is used in which the pumice finds application. It is used in things like roof slabs and overhangs, like the cantilever, seating in a stadium, the deck of some bridges, things that may not require as much load or to burden the entire structure. So that's when lightweight concrete is used. We may talk about this further in another video someday, but moving on, another construction application for igneous rock is masonry stone. Granites often find use here, and they do add a decorative touch to like walls and buildings. And beyond construction, the amorphous solid obsidian, which it was used by ancient nomadic people to fashion cutting tools and arrowheads, and in modern art is also used for decorative aspects. And there are so many other applications of igneous rocks which I know I left out. So geoscientists and engineers, I'd welcome your input. What other applications of igneous rocks can you think of in industry? Please share in the comments. I am sure, as most of you can see by now, we don't just study these rocks arbitrarily. They are very important in our everyday lives. So, rocks don't just tell a story. They are important in industry and in, modern civilization. So, we have come to the end of our little introduction to igneous rocks. We looked at what igneous rocks are, how they form, the different minerals which crystallize at different temperatures from a melt, the Bowen's reaction series, and the societal importance from the beauty and cosmetic industry to construction. There's a lot to igneous rocks, so much of which I haven't covered in this video. But I intend to cover other aspects of them beyond this series. Also, igneous rocks are the result of volcanoes or volcanic activity, but I think volcanoes deserve an episode for themselves in this series. And speaking of the continuation of this series, well, I haven't quite decided what the next episode is going to be yet. It's likely to be one of two things. It will either be on sedimentary rocks or metamorphic rocks. It depends on my mood and what I see in the vision. Whichever one is going to be, please stay tuned for that one. And until next time, please take care. Bye for now.